Yeah, so atmospheric correction of satellite ocean color observations. As you know, that's one of the crucial steps of anything we want to do with this technique because the atmospheric part of the signal we look at is quite significant. And in the lecture, I will go through some of the basics of atmospheric correction, how it is performed, and what it is supposed to do. We'll start as well with the accuracy requirements we have for this, because that's actually the first thing you should always have in mind when you develop any sort of algorithm, by the way, not only atmospheric correction algorithms, is what do you want at the end, and do you need a very high accuracy on your final product, or maybe it's a bit less important. And that may define completely the type of algorithm you develop and the sophistication you may have to include into it. We will go through what this signal at the top of atmosphere is made of, go through some basic principle of this technique of atmospheric correction for ocean color, how it can be still performed with relatively good accuracy sometimes under simplified assumptions, how the modern missions do this, how do we do it at the moment, and basically, whatever it's the NASA, ESA, JAXA missions, ISRO, basically the same, very basic same techniques are used at the moment with various type of implementation, but the basic techniques are basically the same. We will go through what I call here the other terms of the atmospheric correction problem, which are, the kind of perturbations like sun glint, adjacency effects, and so on. Quickly, some of the alternative approach we have as compared to what most of the missions do at the moment. And unfortunately, as well, I will show you where all these algorithms still have some difficulty to perform well in some conditions like, absorbing aerosols, for instance. And something I forgot to say as well is I won't go through, showing you a very long list of different current algorithms and so on. I will concentrate a bit more on the fundamental of the technique and just show you, and I will, of course, there will be a few of the algorithms to illustrate the type of implementations we have. So this plot, which I already used, is just to remind the essence of the problem in some way. That this is the spectra of water-leaving radiance, and you have these two lines, two curves, who represent some of the extreme of what you can observe in the open ocean with chlorophyll 0.01 and chlorophyll 10, showing very clearly the difference in the spectral shape, and that's from that we can derive chlorophyll. And then when you add up the very significant atmospheric signal on top of this, you end up with these two curves, which are quite close one to each other. And that's illustrating the difficulty we have because we want to, of course, discriminate many, many different levels of chlorophyll between these two curves. So we need to do this properly. We need to remove a large contribution as accurately as we can. So this example is just a true color image taken above the Mediterranean Sea. That's a sea with image. What you can see here from the top of the atmosphere is, of course, mostly the atmosphere with, structure with relatively long spatial scales like this haze that we can see here. Maybe some dust there, but nothing that looks like what we want to end up with, which are the structured in the water. So, water-leaving radiances, and here transformed to chlorophyll. And immediately you see all the eddies and filaments and oceanic structures, which are the one we are interested in. Okay, atmospheric correction. So just in a very quick summary of what it is. So we have to estimate this atmospheric path radiance, L path, in order to get to the marine signal, so the water-leaving radiance, LW. That's the goal. And L path is generated by scattering in the atmosphere by molecules and aerosols, and with a component as well of reflection of this or this scattered light at the air-water interface as well. The difficulty is that we don't know a priori when we process an image how much aerosols we have in the atmosphere and what sort of aerosol they are. And we don't have so far any way to have an independent information about this that we could use in the processing. We have to derive this from the signal itself. And the difficulty again is because this path radiance is about 10 times larger than LW. So any error on it will have, of course, a much larger relative effect on LW. Okay, so accuracy requirements. So the historically, which is written here, you know, when we started with the CCTS and the CWIFs, most of the effort and the objective was to derive the chlorophyll concentration. So the accuracy requirements have been defined for this specific objective. Basically, the question at that time was, okay, which errors we can tolerate on the reflectance? So we can, in the blue and the green, so we can derive chlorophyll within, say, plus or minus 30%. And this plus or minus 30%, it's a bit unclear where it came from at the time, but that's basically the accuracy that was expected from in situ measurement as well. You know, from fluorometric determination of chlorophyll in situ was basically around that. So I guess at that time, people thought, okay, at least if we can do as good as we do with in situ measurement, that will be an achievement. And the answer was, roughly speaking, we need 5% uncertainty or error in the blue bands for an oligotrophic ocean. That's this reference from Gordon and Clark, 1981. That's it. That's the only thing and blue bands in oligotrophic ocean means where we have the maximum signal, as you know. Then somewhat more sophisticated requirements were derived for the more recent missions like the MERIS and MODIS. And then it was said, you know, we would like to discriminate 10 values of chlorophyll concentration within each decade from 0.03 to 0.3, 3, and 30 milligram per cubic meter. So 30 value. Okay, that's already a slightly more detailed requirements. And that's what is expressed in the two papers you have the reference below. Just a note on this, you will see that a number of the references in these presentations are, you know, this one is 1999. Well, there was one which is recent, 2018. Many will be relatively old in some way. The thing is, you know, everything has been, you know, put in place basically for the first with the CCTS, but mostly in the CWIFs and MODIS time when they started to, you know, launch and something had to be done. And don't get me wrong, a lot has been done since then, you know, multiple algorithms and techniques have been developed. But, you know, some of these things have been remained, you know, basically the same for that time. So might be time to invent something new. So we'll rely on you for this. Okay, more seriously, this I will go through a bit more through this, you know, the goal to discriminate 10 values of chlorophyll, blah, 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 and see how we could go from this to a requirement in terms of reflectance, because of course, the satellite is not measuring chlorophyll or whatever, it's just measuring radiance. So that's where, of course, you need to have your requirements in terms of geophysical parameter translated into requirements into radiance or reflectance. So we did something, well, you know, relatively simple. So we used the model, bioptical model, and you can use this to plot something like you have here on the top left. So which is basically the reflectance, the spectra, or no, sorry, not the reflectance spectra, that's the reflectance as a function of the chlorophyll concentrations for 4 different wavelengths. 443, 490, 510, and 560. And these little steps you see in the curves are these 30 correspond to the 30 classes of chlorophyll concentration. And as you can see, they are constant in terms of log of chlorophyll. Okay, and then you can simply take this and then derive the plot on the right, which is basically the same, but for the ratio of these reflectance at 443 and 560, or at 490 and 560. So that's typically the sort of blue to green ratio that is going to be used to derive the chlorophyll. And, you know, basically you look at this and you can derive from this what's the error, the maximum error you can tolerate, so that you would make an error of one of these little steps in the curve. Okay, that would tell you, you know, what you need to remain correct. And then you end up with the plots that we have here on the bottom. Well, they are slightly more complicated to explain, but basically then what we did, so from this curve of the reflectance and of their ratio, we quantified the error, that's the maximum error, to make an error of plus or minus one of these little steps, and we ended up with this. Okay, these curves here that you have, so the vertical axis here is this error in reflectance in the blue, 443. And the curve with 1, 2, and 4 corresponds to how large the ratio between the blue and green is, because that has an impact on the way the chlorophyll, the ratio is going to be derived. Anyway, and this continuous curve as well, or when the error in these two bands at 443 and 560 are both of the same sign, both positive or both negative. These two curves here, the dashed one, are if these errors would be of opposite sign. Anyway, the conclusion of this is you see that these numbers here, the delta rho in the blue, are quite small, actually. And that's if the error in the two bands you use for the ratio of opposite sign, it's making things even worse, because you would need them to be very, very small, and actually realistically small, because there is no way you would get to this with your atmospheric correction. But the first lesson from that is you need error of atmospheric correction to be hopefully of the same size, of the same sign, sorry, across the spectrum you want to use. If you start to have, you know, an overestimation in some bands and an underestimation at another band, then it's becoming really hard to derive anything. This is based on the use of a band ratio algorithm, of course. And that's another point I wanted to make, is these accuracy requirements, they all depend as well on the algorithm you're going to use. If we would do the same analysis using a band difference algorithm, we might end up with different values. If we would throw all that stuff, make a lot of simulation, train a whole network with it, and do atmospheric correction, maybe the answer would be again different. So that's the difficulty of the process, is normally, you know, well, not normally, systematically, your accuracy requirements should be attached to the algorithm you are going to use and to what you want to do with the data. So that's the two aspects of it. This is my application. If I want my application to work, I need an uncertainty of, let's say, 5% on the reflectance in the blue. But I need to know as well which algorithm I'm going to use to process the reflectance and to transform this in chlorophyll or sediment or whatever, because that has an impact as well on how much errors I can accept on the reflectance. Oh, yeah, and this is the three values basically that no, not this one. Sorry, these values are just to the the values of these little steps in terms of reflectance. So as you can see, in the blue, 2.5, 10 to the power minus 3, it's not much, but if you go here for large chlorophyll concentrations, you can see that in some bands, it's even much lower than that. And 2 to the power 10 minus 4 is for the band at 560 nanometer. And I put this number because actually this number is very close to, at that time, what the instrument noise equivalent radiance, if you remember that from last week, was defined. So that was already meaning something, that the noise level of the instrument is maybe sometimes already nearly large enough that it might already compromise some of your accuracy requirements for atmospheric correction. So just to, okay, well, that's that to express the difficulty of this. Anyway, so the conclusion of that exercise at that time, well, I guess I already said that more or less, that the first requirement, so retrieval of 30 reflectance values, requires that atmospheric correction errors be maintained within plus or minus 1, 2 to the power of 10 minus 3 at 443 nanometer, within plus or minus 5, 10 to the power minus 4 at 490, and so on. And yeah, sorry, that's what I just said, that this value here at 560 is nearly equal to the noise equivalent reflectance specified for Meris. Okay, but we can skip this. This is not really important. It's a bit detailed. And when these values, which so far are expressed in terms of reflectance, are expressed as relative errors, they could represent 1% of the normalized oceanic reflectance at 443 nanometer and up to 215, except when the chlorophyll is going to be quite large. That's the challenge we have. Again, keep in mind when we use a band ratio, when the chlorophyll is large, the reflectance in the blue is becoming very low. It's not changing much, so it's making the algorithm very sensitive to any error. Yeah, and the last point, errors have to be of the same sign at all wavelengths, otherwise you are a bit in trouble. But all of this was just for one case. I work in the open ocean. I use a blue to green band ratio to derive chlorophyll. Well, which is basically, what the OCR, all the algorithm, the MODIS, and so on do. But what about other applications? SPM in turbid waters, phytoplankton functional types, IOPs, and so on. And well, the situation is that basically we do not have any detailed requirements for this other use of ocean color. Okay. But again, you can see in this paper by Wong and Gordon, 2018, that there is a bit of this that they started to try to do. So I guess the message here is, again, yeah, that's maybe the work you have to do at some point when you think to developing maybe or improving algorithm for atmospheric correction and so on, or even before you think to atmospheric correction, even if you want to derive this kind of advanced parameter, if you want, in the formation color. Yeah, you really need to think in terms of what you're going to do, the accuracy you need, and using some model to transfer this into errors in reflectance that you can tolerate in your system. There is a sort of corollary question at the bottom: is my sensor worth it? Do I need to do a sophisticated atmospheric correction algorithm if my sensor does not have the high radiometric accuracy that I need? So it's all, again, story of uncertainties in your measurements, in your algorithms, and how all these things combine. And yeah, so sometimes you could just be okay with a very crude atmospheric correction because it's just a waste of time to try doing more if your sensor is not adapted to this. What time is it? Okay, well, we have a bit of time. Okay. Any question at this stage, by the way? You know, I didn't remind this many times, but you can, yeah, and at any time during this talk to ask any questions. So, nope, all good. Well, let's continue. So let's go back now to the signal. So what is making this top of atmosphere total radiance? So this kind of graph is supposed to illustrate this. So you have the sensor here, the sun. This is the RC interface. And that's supposed to represent the main sorts of interactions in the atmosphere and with the interface that are going to lead to this signal you get here. So the one we are interested in is the little a here. That's the water leaving radiance, which is coming here, part of it being attenuated along the way, and some of this getting to the atmosphere, to the sensor. And then you have all these possible atmospheric interactions. So where is B? Yeah, not something, but anyway, all these things, you know, you can, I don't need to go into details. I get you get that. Single scattering like H here, just going back to the sensor, a single scattering here, and a reflection at the surface, and so on. So all these things are getting together to generate your signal. And the way we generally express it is this one. Again, make a small warning here. Splitting a radiance like this into different components, this is normally not physically valid. Physically speaking, you cannot do this. So that's an operational way to decompose the signal and to try to do something with this. IOPs are additives, but not the radiometric quantities. Okay, so what do we have here? L with this small R subscript, so that's for the Rayleigh molecular scattering. So we will go into this, all of these terms in detail afterwards. So aerosol, RA is for the coupling between molecular and aerosol scattering. There is no reason that photons are just either scattered by molecule or by aerosol. They can do both, of course. The sun glints, white caps at the surface, the water leaving signal we're interested in, and this small t and capital T for transmittance. So the big T is for the direct, what we call a direct transmittance. So transmittance of the very sort of a collimated light, you know, like the direct sun glint, and the small t as what we call diffuse transmittance of a diffuse signal across the atmosphere. And again, the geometry, we have seen this a number of times now, so I don't need to dwell on this too much, but okay, the three angles, sun zenith angle, satellite view angle, and the azimuth difference, or relative azimuth, as we call it, between the sun and the view. Two concepts which are used very often in this domain. The first one is the optical thickness. So that's a dimensionless quantity related to how much attenuation occurs in the entire atmosphere. And again, you can define this for just molecular scattering, aerosol, or everything. And the single scattering albedo, so B over C, so scattering over attenuation, which is as well dimensionless, and which is one if there is no absorption. So there are quantities very often used in the atmospheric correction domain. Molecular scattering. So that's one of the largest contribution to the total signal, at least in the visible part. The optical thickness of it can be represented this way. It's exponential, no, not exponentially, increasing toward the blue as a polar law. And importantly, to keep in mind is that the Rayleigh scattering function is symmetrical with respect to the direction of propagation. Okay, but probably you have seen this quite a number of times, but anyway, and here you have example of this optical thickness from the blue to the infrared. So in the blue, 0.3 is really definitely a large optical thickness as compared to what you have here. That means basically the relay component is the one that is very important in the blue-green and becoming very small when you go to the near-infrared, and the aerosol component is going to be much more important in the near-infrared. So again, there is one way to express this when you consider, you make the assumption of a single scattering regime, which means basically the atmosphere is clear enough that you can make this assumption that most of the scattering is single scattering. This is the equation you have, and the three terms A, B, C represent these three possible interactions. So one scattering in the atmosphere, and that's it. The other one is one scattering, then a reflection at the interface, and then go back to the sensor. And the other one is first reflection at the surface and one scattering back to the sensor. Well, that has been used quite a bit in the early days of ocean color. And again, what you have here, well, you recognize all the optical thickness, the mu are the cosines of the angle, so view and sun. This omega, which is this here, the single scattering albedo, and F naught, which is the extraterrestrial irradiance. And then the PR that you have here is the phase function, and the rho F is the reflection coefficient at the interface of the term B and C. Okay. Of course, this is for single scattering. If you want to be a bit more, significantly more accurate than this and more realistic, because most of the time there is anyway some multiple scattering and sometimes quite a lot, then you need to go through additive transfer to calculate this, and that's what John has been showing you last week. And then what you will need to consider, wavelength of the optical thickness, geometry of the problem, of course, the actual atmospheric pressure, because that's defining how much molecules you have in a given atmospheric column, and the wind speed, surface roughness, polarization if you have a vector code. And from this, you can build, and that's what all the current mission processing do. You build the big lookup tables of this, the function of wavelength, geometry, pressure on the wind, and to process every pixel, you go into this, you interpolate, and you get your value of the relay scattering. This one is just to illustrate again that LR is a large contribution to the total signal. So the vertical axis here is the top of atmosphere reflectance from 400 to 900 nanometer. That's, for some sort of maritime aerosol model, a relatively low optical thickness, and the geometry is indicated here, but whatever. And so you have the blue curve, which is the total reflectance, and the green curve, which is the relay reflectance. As you can see, they both follow a relatively similar shape because ρr is a big contribution to it. And this red curve here is with the vertical axis on the right. So that's the ratio of ρr upon ρt. Okay, and you can see that in the blue, we're close to 80%. Here we are down to 50% maybe. How does it look in the SWAS? And that's, John said last week that using additive transfer is a good way as well to try to understand how all these things vary and to get a sense of, when I change this parameter, what's happening to my reflectance and so on. That's what is basically illustrated here. So what you have on this kind of plot is the variation in the SWAS. So the horizontal axis here is the view angle from 0 to 60 in that part and 0 to 60 here. But for these two planes, the solar plane and the anti-solar plane, so the solar plane when you are basically looking in the direction of the sun, the anti-solar plane is 180 degrees away of this. And the panel on the right is for the perpendicular plane at 90 degrees. And the Rayleigh reflectance here is this curve that you have here, which is, as you can see, quite smooth because of this relatively not isotropic, but symmetrical scattering in the forward and backward direction. It's not symmetrical in the two planes just because in that situation, the sun is at 40 degrees. The sun would be at zenith. You would have a perfectly symmetrical curve in the two planes, of course. Okay. But, you know, what you see here as well, of course, is an increase of the signal as you go to larger view angle, of course, because you look across a longer path in the atmosphere. Aerosol scattering now. So, of course, LA proportional to the amount of aerosol particles in the atmosphere to a first degree, unknown a priori, and the optical properties are determined by the composition of this aerosol. So again, refractive index and particle size distribution. Scattering by particles with size lower or similar to the wavelengths. So that's what we have on the aerosol. So their optical properties can be computed through the theory. And that again, most of the time, what is done to generate lookup tables and analyze ocean color or whatever is optical properties of aerosols are based on the Mie theorem, which is, as you probably know, normally valid for spherical homogeneous particles, which aerosols are not. But, you know, it's generally good enough approximations. Or sometimes we use different techniques, you know, but most of the time it's still done with the Mie theory. And because the average particle size are close to the visible wavelengths, so the scattering for this aerosol is highly peaked in the forward direction, like for phytoplankton in the sea. So size distributions. So you have here two examples. On the left, for purely what we call purely maritime type of aerosol, and on the right, urban industrial type. I guess the one we have in the atmosphere these days here. The main difference, okay, the horizontal axis is the radius of particles, and the vertical axis is their distribution in terms of volume. Well, you clearly see the difference. For the maritime type, there is little small particles and a relatively large amount of large particles. And it's exactly the opposite for this one. And so basically what you can keep in mind is the more small particles you have, the more selective will be scattering, meaning the spectral dependence of scattering will increase as a function of the proportion of small particles. So again, urban, industrial, dust type have quite a lot of these small particles. So the scattering is increasing a lot toward the blue. And that's what is generating this kind of milky atmosphere we have. And in the opposite way, maritime aerosols have sometimes a nearly neutral scattering, you know, with nearly no spectral dependence of scattering or relatively small dependence of scattering. The refractive indices, well, they are depending again on that's measured done on different sites. I think it's mostly this one on terrestrial kind of continental aerosols, but quite often, you know, it's in the range, it's around 1.5. It's generally not very, very far from that. And well, that's a bit the same, but that's this single scattering albedo, so B over C. You have 4 types, so clean atmosphere, standard, a mixture of this and a dusty atmosphere. So the top one is again the size distribution, and the bottom one is this single scattering albedo. So for mine, 1 means no absorption at all. So in that case, you know, there is, it's extremely rare that we have this B over C, which is exactly 1. There is always some kind of absorption, even for clean maritime atmosphere. But it's generally negligible anyway. But then you can, you know, when you reach this kind of aerosol, you see that you can go down to 0.8, for instance, which is 0.8 for the single scattering albedo means you already have quite a lot of absorption. And volume scattering functions, typically, but this is a number of examples here. Always the same sort of shape with a very large forward peak, especially for the maritime aerosols with this significant proportion of large particles. As you can see, sometimes if you go to the one on the bottom right, the volcanic ash, the forward peak is definitely much smaller, which means you have less of these large particles. I guess that's when this volcanic ash has been is of some age, so the largest particles have settled, and you remain in the high atmosphere with only the small ones. Okay. Yeah, one thing which is important is for the maritime type, and of course, sorry, one thing, all these curves are based on models, okay? So a size distribution, a refractive index, meteory, and you end up with these curves, okay? And the percent that you see here for the maritime models is the relative humidity in the atmosphere, because the size of particles will depend on the relative humidity. And if I am correct, the particles can grow if they in the more humid atmosphere, and then you end up with an even more forwardly peaked VSF. And you see on the bottom right, it's said that this is for 550 nanometer. That's the volume scattering function, so that's in per meter per steradian. If we would normalize by the total scattering coefficient, so we would have the phase function. The phase function would not be changing much with wavelength, okay? The VSF change because that's the absolute scattering, but if you normalize by the total scattering, go to the phase function, these curves would not change much with wavelength. Change a bit, but not much. And okay, you recognize the same equation that we had for the molecular scattering in the single scattering approximation, same equations, but you just, by the way, there is a mistake on this plot because the tau R and all the R should be A, of course, on this one. Sorry for that. So that's LA equal, you know, all the subscript R should be replaced by subscript A. I will correct that in the slide later. But that's exactly the same equation that for the aerosol scattering, for the molecular scattering. Okay, again, similarly to the relay, well, you can, of course, compute this through additive transfer in order to include all orders of scattering if you don't want to use this approximation of single scattering. And again, then you need to choose an aerosol model. So particle size distribution, again, refractive index, and then VSF, or phase function. The aerosol optical thickness across the spectrum, the geometry, again, wind speed, and so on. So same thing. And again, you can use any sort of additive transfer to derive this. And if you need, you can generate a lookup table of your aerosol signal. There will be a few more parameters, of course, than for the relay, because you need to know the aerosol type, not only the optical thickness. So that can quickly grow into a relatively large sets of calculations. Okay, now that's the same plot I showed you a bit before, but now we look at the aerosol signal. This is the row A that you have here, which is coming here, going to this peak, going down again, and here. And here on the other plane, and here. So as you can see, well, as compared to the relay reflectance, that's absolutely not the same shape. Any idea? Yeah, I have a question for you. Any idea what this peak in the aerosol reflectance is coming from? You can say anything, you know, won't be taken against you. No, I mean, that's okay. Nope. Maybe, okay. Okay, just trying to remind aerosols like, you know, phytoplankton, whatever, phase function is very forwardly peaked. So sunlight, here the sun is at 40 degrees in the atmosphere. There is a lot of this which is going to scattered forward, so basically toward the ocean surface. And then it's going to be reflected at the surface and then spread again by scattering. So that's what you see in this peak, okay? You don't have this in the Rayleigh because the Rayleigh scattering is way larger. The phase function is not forwardly peaked like this. So the signal, the scattering is all directions. So there is no effect like this of a significant signal being reflected at the surface. So that's what you have in the aerosol reflectance here. The small bump in the other plane is still due to backscattering, direct backscattering from the aerosol as well. Okay, and in the perpendicular plane, however, you are away from this direct image of the sun and so on. Then you go back to a relatively, you know, smooth signal. So you can imagine from this curve, you can try to get a sense of the, you know, when your sensor is looking in all sorts of directions toward the surface, what sort of aerosol contribution is going to be part of the total signal. Okay, now, well, aerosol on one side and molecules on the other side, that's fine. That's a way to, but that's of course not what happens in the real atmosphere, everything together. And as we said, there are some interactions between the two. And that's what is illustrated on this graph. So it's again the same representation, you know, with the three planes, solar plane, anti-solar plane, and perpendicular plane. Same plot, but now we can look at the dotted curves instead of looking at this continuous curve. And so you have a dotted curve again for which is this rho star R for the Rayleigh reflectance, and this rho star A for the aerosol reflectance. And as you can see, star A, and where is the vortex? Yeah, and the rho pass, the total is still the same on the top. So these dotted curves, they are the aerosol and Rayleigh components, but calculated with a mixed atmosphere, okay? The one I showed you so far were considering either of the two components. And what you can see, well, the overall shape is the same, but the values are different. And why is this? Is because, of course, when you have the two, you may have some part of the signal just purely being scattered on molecules, one part of the signal being purely scattered on aerosols, but you have one part of the signal which is scattered on both. And of course, if you just look at the two separate ones, you will get lower values than what you had calculated before by separating the two and ignoring this interaction between aerosol and molecules. And this combined signal is the one which is represented on the bottom panel, this rho star RA, so RA for Rayleigh and aerosols. And well, you can see it has a very, that's something we never really understood, by the way, or understood or really well explained, is why this one has this very symmetrical, nice shape like this. And just one parenthesis, to get to this result, we had to use a Monte Carlo technique. That's the only way with the Monte Carlo that you can count your photons and know exactly whether a photon has been scattered once on a molecule, once on aerosol, only on aerosol, whether it's a single, double, three, scattering, whatever. You can count all these things. And then you can analyze the different parts of the signal. Anyway, so this is just to for you to keep in mind that, you know, this very first equation I showed you at the beginning, and I warn you that this is not physically valid actually, because we cannot physically normally split a radiance, any radiometric quantity, into components. And that's basically what is expressed in this graph as well. So you need to consider, to keep in mind that there is an interaction between the two, and it has to be taken into account in some way. The thing is, very often it's done as a corrective term. So what is done is calculate the aerosol reflectance, the Rayleigh reflectance, and then there is a corrective term which is added to this to account for this interaction. But this corrective term then is not physical, and you can look, it's illustrated here by this dotted curve. It's kind of a weird shape. It can be negative sometimes. So it's not physical, just a correction which is introduced in the system. Okay. Just let me check where I am in the photo. Oh, yeah, no. Yeah. What time is it? Yeah, okay, that should be fine. Well, that's just a further illustration of the, you know, how the signal is changing with when you have all this mixture of aerosol and molecules. And as a function of the optical thickness. So in that case, you have on each of these plots, you have 4 curves, and they correspond to aerosol optical thickness from 0.05 to 0.5. And well, you just can see the increase of the signal. In that case, the sun is at 60 degrees, and you see the peak at 60 degrees on the left side. And so the top plot is for the path reflectance. The next one is this pure Rayleigh scattering. Next one is the pure aerosol, and the one on the bottom is this interaction between the two. Well, that's it. Nothing more to say on this. This one is for to illustrate again the spectral dependence of the various terms. As you can see, we know that the Rayleigh reflectance with this optical thickness going in lambda to the power -4, more or less. The aerosol, which is a bit flatter in that case, it's probably a maritime atmosphere. And the interaction component between the two, which is in terms of spectral change, is mostly following the Rayleigh scattering. And to finish with this, that's another way to represent this. Again, that's from this Monte Carlo analysis we did. So what you have here, on the top, that's for the blue band for 45 nanometer. On the bottom, it's in the near infrared. And here, this little bar histograms in some way are looking at, okay, here, if you have an atmosphere of molecules only, what's the proportion of single scattering, double scattering, 3 scattering, 4 scattering, and so on. So, and here it's if you would have a theoretical purely aerosol atmosphere, and here it's the chessboard is for when you have both together. Okay. So what you can see that single scattering, as we said, is, and that's even for an aerosol optical thickness of 0.3, which is quite significant. You still have 70% of the signal, which is single scattering. Okay. Of course, when you merge everything together, this one for the single scattering comes down to 40%. Okay. So you can look at these numbers. And then for the near infrared, as you can see, in a purely molecular atmosphere, 95% of the signal is single scattering as well. So that's why, sometimes the single scattering approximation can work, because that's most of the signal. Okay, so we have had this look into the different components. So we now go back to this, decomposition of the signal. So we have some ideas now how the LR, LA, LRA, blah, 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 are formed and what they look like and how they vary and so on. So now we need a practical way to determine all of that stuff. So basically, and that's always what you will have to do, the thing is you need to play with the spectral information you have. And of course, to use atmospheric transmission windows, you don't want to try to look and use bands where there is too much atmosphere absorption, because that's going to make the things way more complicated or even impossible. And that's what you're going to use to, disentangle these various components. The good news is at least the Rayleigh component, you can calculate this a priori. You just need to know the atmospheric pressure. But as we said in introduction, unfortunately, the aerosols are highly variable in the oceanic environments, and then you don't know about them. So what can we do? Okay, so we need to eliminate some terms to get access to the others. And again, the term on the right here, that's G for the sun glint, WC for the whitecaps. So the first thing you can do, and that you do, is to just you don't do this atmospheric correction in a geometry where you're looking at the sun glint. Generally, you just avoid doing this. The other thing you can do is to avoid the high wind speed situations. Sometimes you can't. Okay, and of course you don't necessarily know a priori what the wind speed is. That's where you need some auxiliary data to tell you. And if the wind speed is high, well, you will do something anyway. But at least for the purpose of the logic of all of this, you can start by saying, I'm not looking at the sun glint, so this term is 0. Wind speed is low enough that I don't have any whitecap at the surface, so this is 0 as well. So but then, okay, we still have 4 terms. It's a bit too many. So what can we do? Well, we will use this black pixel assumption. The plot here is the absorption spectrum of water across the spectrum, so from the 350 to the near infrared. What you know is water absorption is high enough in the near infrared that very few photons can escape the medium, at least when the scattering is relatively low. So that's generally true in case 1 waters, as far as the particle content remains relatively low. That's actually not true when you have, something like 10 milligrams of chlorophyll, or even maybe a bit less than that. So yeah, that's very high here. So basically, LW is 0 for wavelengths above maybe 750 nanometer. Again, of course, for the open ocean situations. So what can you do? Well, remove this. Okay. So you end up with a bit one less term. This one you can calculate. So okay, finally you get to LA plus LRA, which is what is left. But then, of course, you do this in the near infrared because that's where you don't have the LW. But that's not what you want, because what you want is to correct for the visible band, of course. So yeah, what we need is the aerosol signal in the visible so that we can get LW there. So what you have to do is to infer this aerosol signal in the visible from their values in the near infrared. So that's basically what the atmospheric correction is all about, and that's the critical step. So all sorts of techniques you can imagine to do this, but let's have a look initially when you go back to this assumption of single scattering. So again, the same equation. The good thing is this equation can be simplified. If you make the assumption that the optical thickness is small, these terms, which are expressed as a 1 minus exponential of e of minus x, would tend to be equal to x. So the equation is simplified this way, okay? And some of these terms are expressed here. So optical thickness, angles, phase function, and reflection coefficient. So you can derive the same for the aerosol, and that's a very quick and easy way to do this. And yeah, but then, of course, the question is, and it's kind of a small parenthesis, but it's, by the way, what if you do not have near-infrared bands? And I have put in brackets CZCS because that was the situation we had initially with the CZCS. But that might be actually still the same thing, you know, when you want to use, you know, what I would call the non-ideal ocean color sensors, you know, sometimes this very high resolution system that people try to use, they don't necessarily have the appropriate bands. So you might end up in some situation similar to what we had at that time. In that case, that was the concept that was developed. And again, that's valid for open ocean only, this clear water radiance concept, which basically says that the water leaving radiance at 550, or the reflectance, if you want, is nearly a constant over clear waters. So you can set a value and then use it as a fixed point to determine your aerosols. And they were extending in some way the concept of no signal in the near infrared to no signal in the red at 670. Of course, these assumptions completely fall in a number of situations, but actually that was working. And I thought I had this. Yeah. That's just an example of CZCS data processed through this way with the aerosol radiance derived on the top and the water leaving signal on the bottom. So this, you know, again, the discrimination between the correction of this atmospheric effect, which is completely masking what is below, was working quite okay. Yeah, and I mentioned this one because this one is, okay, clear water radiance concept to say reflectance at 550 is constant, but you can try to do something a bit more, slightly more sophisticated by saying, look, I know well enough about how the reflectance is changing with chlorophyll. I have a bioptical model, so I'm going to use this instead. And that's what was done, well, quite a bit of time ago, but that was quite used, is to extend this concept now. You still don't have any near-infrared bands, but you're going to model the reflectance in the visible band. So, of course, you don't know a priori what the chlorophyll is. So you make a guess, calculate the reflectance, and you try iteratively to progressively disentangle the atmospheric and the oceanic part. And that's actually still used, and I will come to this probably in the second part of this lecture. That's a concept that's basically the basis of what would be called the spectral matching or something like this, and that has been very much used and still used these days. Okay, I'm just trying to see if I'm more or less. No, I will continue a bit before we make a pause. Okay, now, what if you have the near-infrared bands, which is indeed what we have now? That started with C-waves, and all sensors since then have at least 2 near-infrared bands to do this. So no longer need to make any assumptions that LW is constant at 550 or that you can model it or whatever. You can completely split the problem and do the atmospheric correction independently of knowing anything about the biological properties of the ocean you're looking at. So what is done is to determine this epsilon. That's the notation they decided to use at that time from 2 near-infrared bands, which is just basically the ratio of the atmospheric of the aerosol signal in these 2 near-infrared bands. And then you assume that there is a relationship at the function of an exponent n to extrapolate this to any other wavelength. And well, this relationship is not exactly what happened in the real world. These curves which express this spectral dependence of the aerosol signal with respect to a given wavelength, okay? And this one is actually, it's in log, I don't know why they have put that in a log 10, yeah. Well, maybe yes, to the difference between the exponents, and that's 865 normally, okay? So, you know, they are not really straight lines. There is some, so that's again, somewhat a simplification of the truth, but, you know, you have to do something. So because it's not really like this, then people started to think, okay, we need to do a bit better than that. Okay. Single scattering approximation does not allow reaching the accuracy we need. That was the first motivation to do better, to do differently than what I showed you so far. And that's when the use of aerosol models has been introduced to perform the atmospheric correction. Because, you know, in all these things I showed you before, there is no aerosol model, nothing like this. Just try to use directly the signal and see if you can do something from it. What an aerosol model is, again, it's just particle size distribution and refractive index. And from this, meteory can be used to calculate all the optical properties, and then you can generate, you know, lookup tables or directly calculate your signal. Well, that's what we have seen before. So that's just a reminder. Particle size distribution, very different. So that's really the critical information to include. And well, that's what I can skip. I've seen that already. What we didn't mention is, okay, you can select a model, do all sorts of radiative transfer calculations, but the other thing you need to know is where these aerosols are in the atmosphere. And this image is a LiDAR profile showing, you know, different layers in the atmosphere. So the altitude is from 0 to 20 kilometers. This is a smoke plume. This is a dust plume, and so on. But here you have some clouds as well. Fortunately, we don't need to care about this when the aerosols are not absorbing. Okay, it's been shown, can do this again by radiative transfer or some simple calculations. If there is no absorption by aerosols, you can basically distribute them in any way in the atmosphere. At the end, the top of atmosphere signal you will get will be the same, to within a few percent maybe, but basically or even less than that. Except if you would make something completely crazy, like putting all your aerosol in the top of the atmosphere, which of course is not happening, you may have something a bit different. But if you make a reasonable assumption about an average distribution in the atmosphere, that's okay as far as they don't absorb. As soon as the aerosols are absorbing, then that's when you need to know more or less where they are in the atmosphere. And that's because, you know, if they absorb, if they are relatively in the lower atmosphere, there will be a lot of interaction with relay because there are more molecules there, so there is more possibility of absorptions than if they are in the top of the atmosphere. So that's changing completely the interaction with molecular scattering, and that's changing the signal. Okay, I guess that's what I said in this slide. So I have a bit anticipated. Fortunately, when aerosols do not absorb, their repartition with altitude does not matter much. So that's just a typical example of vertical profile that we used in some radiative transfer calculations with the big thick line is for the aerosols, like this, like this, like this, and like that, just because we decided at that time to use different aerosol types in the lower boundary layer in the troposphere, in the stratosphere. But you can do all sorts of different things. You can make a smoother profile if you want. That doesn't matter much. Okay, so kind of summary at this point. We have considered a situation where we can ignore the glint and the white caps. Then we said we can use the black pixel assumption, so no signal in the near infrared. So we can determine the aerosol signal at near infrared bands, and we don't know how to compute the relay in a multiple scattering regime. We also know how to compute the aerosol in a multiple scattering as well. We still do not know how to use this to go to the visible bands. So you remember this plot I showed you already. So that's the spectral dependence of the aerosol signal. In that case, they try to model it as an exponential with small coefficients. That's the very first algorithm that was proposed for the C-waves. In that case, the thing is, okay, sorry, another illustration of this, same thing, with a slightly larger range of variability. All these curves for these different, the O99, N50, blah, 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 they are all different aerosol models. And as you can see, the spectral dependence can be really, really very different from this one. The T50 means it's a terrestrial type of aerosol with 50% relative humidity. So a lot of small particles and a very strong spectral dependence increasing toward the blue. At the nearly opposite, these squares here for the, it's probably the maritime with 99% humidity. So quite a lot of large particles. So nearly no spectral dependence of scattering. So again, we have information from two bands in the near infrared. And that's what we are going to use. We need to, from these two measurements, to decide, which one of this aerosol model is probably the most relevant to our situation. And doing this, of course, on a pixel per pixel basis. Yeah, so that's basically what was introduced by Gordon and Wang for C-waves. So you start to calculate what they start to do. They start to remove the relay reflectance from the top of atmosphere reflectance. Let's get rid of this. So doing this, they can determine this epsilon using two near infrared bands. Then they can navigate the lookup table they have generated before to find the two closest value, and they will use this to select what they call the two bracketing aerosol models. Basically, if they find that the epsilon is between these two curves, they will say that the T99 and T50 or whatever it is on the plot are the two bracketing models. So I know that I'm falling in between these two curves, so I can use these two curves to extrapolate to the visible. The other thing you need to know, of course, you want to know where you are between these two curves. Or am I just at the middle, or am I closest to this one or that one? So that's what they call the mixing ratio. And with this, you can extrapolate to the visible, and then you have your atmospheric contribution in the visible, you remove it, and you get to LW. Yeah, one thing you have to assume is that these curves do not cross, of course. Because if you think, oh, I am in between these two aerosols, but this, whoops. I don't know. No. Okay. Yeah, that would be a problem. Okay. So that's basically what was introduced for C-Waves, and that's still exactly what is done for MODIS, for PACE, for all-sheet, SGLI, OCM3, whatever. That's the basis of the, it's exactly this, you know? Yes, essentially. Implementations vary, that's where all the details, which are not necessarily the most important for today, are going to come, but this is basically what is done. Slight difference for the MERIS and what is now the algorithm for the OLC. That might change. I think the UMEDSAT have decided to maybe change this for the next reprocessing. We will see what they do. But maybe that still be essentially based on the same story. Is in the case of the C-Waves MODIS technique, they start by doing total signal minus the relay, and then what is left is supposed to be the aerosol component. For MERIS, we decided to do the ratio instead. We thought, well, that's maybe somewhat more physical sense. So total path radiance, what the measurement, divided by the relay. So basically, that tells you the increase of the signal that's as compared to a pure relay atmosphere, which is coming because you have aerosol in the atmosphere. So I might not need to go into the details of this, and anyway, it'll be very soon time for a break. But that's what we did, or I can quickly go through this. It's a bit the same logic. So we start at 865 nanometers, so that's the first near-infrared band. So you have raw pass, that's your measurements, and you calculate raw R, you make the ratio of the two. You get some value, maybe 4. Yeah. And then these curves here, that's what you have in your lookup tables, because you have calculated this for all sorts of aerosol models. Here I have only put 4. Okay, the horizontal axis, sorry, is the optical thickness. And you know what you do, you go into this and you say, okay, if this aerosol would be the one actually present in the atmosphere, this is what the optical thickness would be. If this is this model, this is what optical thickness would be, and so on. So you get a number of possible values of optical thickness, then you transfer them to the next wavelength, 775. And you can do that because they are aerosol model, you know their spectral dependence, so you can move the value to 775, and then you do the opposite way. You say, okay, if the optical thickness is this, these aerosol models tell me that the ratio raw pass upon R should be this. Then you end up with a number of these raw pass upon raw R ratios, and you compare it to the actual one that you have from your measurements. And then you can see, again, find these two bracketing aerosols, which are the closest to the measurements. And then here you go, you're done. You can extrapolate this to the PCB. And whatever you do this, C-Waves, MODIS, MERIS, JLI, and all the new things, they more or less all perform the same way. That's what you have on this plot. That's from an exercise, an intercomparison exercise we did some time ago. So the two top plots are just the ratio of the LW at 443 from the algorithm to compare to the true. Of course, this one is an intercomparison exercise based on simulated data, so we know what the true value is. And the horizontal axis is the air mass. So the air mass is 1 over the cosine of the sending angle plus 1 over the cosine of the view angle. That's basically telling you how long the path in the atmosphere has been from the sun to the sensor. And you have 4 algorithms which have been compared there. So you can see that basically up to an air mass of maybe 3.54, they all are relatively consistent. Then there is a spread of the value for the larger air mass, because it's always when the air mass is becoming larger, that uncertainties are increasing. And so that's for 43 and 490 nanometer. And the one on the bottom is the same, but looking at the ratio 443 to 555, because again, that's very often the one we use to derive chlorophyll. And in terms of deriving the ratio, they are all quite good, quite consistent. But again, things start to diverge from an air mass of 4, more or less. That is sometimes, yeah. Well, that could be, all this radiative transfer, because this is based on the simulated data. As John said last week, it's plain parallel assumption, okay? And we know that this becomes really not very accurate when the sun zenith angle is too high or the view angle is too large. And that's what you can expect then to see in these results, that the algorithms are going to have a hard time and they diverge and the results are not so good. In that case, it's not really true because it's based on everything is based on the radiative transfer. There is no real observation into this. But that already means that anyway, these various algorithms are not performing that well when the sun zenith angle is large and the view angle is large. And that's a remaining difficulty of any atmospheric correction algorithm at the time. Okay, so let's restart. So we stopped on this slide, which was expressing basically showing you the generic performance of this type of algorithm that we have been using for a while. The general difficulty that when it comes to large sun angles or view angles, it's where the spreads between these different techniques can happen. That might depend on the type of implementation they have been using, what sort of radiative transfer code they use, what sort of aerosol models, many sources of uncertainties, that we have in this kind of process. But, the thing is, this works quite well. I mean, if you consider the success of all these missions and considering the challenge of extracting a quite small signal from the top of atmosphere signal, that's actually a very big achievement. Okay, we're going to look at a few of these things we have ignored so far to make the problem a bit simpler. But anyway, they are there. We need to cope with them in some way. And the first one is this sun glint. So sun glint is basically the specular reflection of the direct sun beam at the surface. And that's occupying quite a significant part of an orbit, of an orbiting system like the one we use, when it comes to the situation where the position of the sun is such that in some of the view angles of the satellite, you are just looking into this specular reflection. So you have a huge signal. So the sensor is sometimes even saturating. And so what can we do? Because, of course, you can simply say, well, let's get rid of this. Any geometry with some sun glint, I get rid of them. But, you would eliminate quite a significant amount of data. So maybe you can do a bit better. So again, we go back to this Cox and Munk model that John introduced and which is still in use in, I think, all current processing chains for atmospheric correction. So it's basically, well, it's a simple equation that is deriving from the wind speed W here, this sigma square, which is the probability distribution of the wave slopes, and then you can derive analytically what the glint reflectance would be, knowing this geometry and this sigma, which is here, okay? So you can do this. Of course, the statistical representation that Cox-Munk allow you to derive is a statistical information. So as any statistical representation, it cannot be always accurate and always exactly representative of what's happening in the real world, but it has proven to be still quite efficient. Okay, so this is an illustration of this sun glitch signal as a function of the sensor view angle on the horizontal axis, and for different this delta phi. So remember the azimuth, the relative azimuth, the azimuth difference between the sun and the sensor, and no, it's a bit more complicated than that. So I did not enter into it's the complicated geometry you have on the little plot here. Beta, which one is this one? I think it's the, that's going to be, yes, it's the scattering angle, but with respect to the slope, to the orientation of the facet at the interface, if I'm correct. But yeah, I think that's what it is. Okay. Generally on each of these slides, there is a reference and, yes, nearly. And so you can get there and get the details if you need, of course. So this one is just expressing, I think here the delta phi equals 0 is used for this, the worst situation where you look at the sun. That's something that has been confusing many people in this arena, that sometimes the convention in between, that is used to express when you look in the solar plane and you look at basically at the sun glint, it's generally, it's quite often used for delta phi equal 180 or 0, depending on some convention. So it might be sometimes confusing, but here, because that's the maximum curve, that's of course the one where you look at the sun. Okay, but that's just to express the fact that it's a very significant signal. And the other way to look at this is looking at an image. I think this one is, I think it's a MODIS. It's probably a MODIS image. So you have, it's part of the swath, and of course you clearly see on the left part this huge signal, and the 3 plots on the right side are just line across this image and showing this big bump because of the sun glint. And other illustrations when you look at this kind of images. This one I wanted to show it because there is the ideal representation of sun glint modeled by nice equations. This one, which is open ocean situation. So again, if you model this from the equation shown before, that's going to match probably very well. This one's in particular, the one on the top right and the bottom left. There are situations where, well, there is something that is that's not really following this nice geometry. And it's because you have land in this area, you may have local effects. So the relationship between the wind and this distribution of waves and facets is no longer really, following this nice geometry. So that's one of the difficulties. You can see it on the one on the bottom here. You have the island of Crete here in the Mediterranean Sea, and there is we are in the sun glint area, but you can see definitely that it's some areas where there is no sun glint. It's darker. Maybe just because, with the wind blowing from the north, maybe, and there are some island effect, you end up with very, very cold waters in the middle of this. Well, this one won't have it, of course, the same sun glint pattern. So that means local effects and relatively smaller scale variability in the wind pattern are going to generate this. And if you would like to correct this very properly from your images, you would need to have a very good auxiliary data telling you what the wind speed is. And even more than the wind speed, actually, some of the algorithms use as well the wind direction, because that's going to change a bit the pattern as well. Yeah, that's what I should remind is the equation on this slide is the one for which is ignoring the wind speed direction. So it's a completely isotropic model. Equation becomes a bit more complicated when you take the wind direction into account. Of course, what you can do as well is to try to minimize the impact of sun glints in your data. And then you need to tilt your instrument a bit. That's what most instruments do, not all. On the right side, it's just a plot of the C-wave sensor, but the pace is doing the same and so on. It's a long track tilt. So, the sensor is tilting plus or minus 20 degrees when it comes to the part of the orbit where there is a risk of sun glint. And that helps to change a bit the geometry and to minimize the impact, to reduce in the image. It's reducing the area where sun glint is important. The other way of doing this is on the left side here. It's what the Sentinel do. The tilt is across track. That's another way. So basically, instead of looking symmetrically to nadir and having a large part of your swath contaminated by sun glint, you just tilt your instrument a bit away from the sun glint and you have less of this. That means, of course, your track is a bit asymmetrical, and on one part of the track, you're going to have relatively large view angles because you tilt your instrument. So that's the two main ways to practically minimize the sun glint impact. Okay, second term we neglected so far, but which exists on these white caps. I put 3 illustrations on top of how white the sea can become when the wind speed is significant. Of course, the one on the completely on the right, I guess, well, you can forget about doing any ocean color in that case. It's becoming really, really messy. But then, even when it's not as critical as this, it's still an issue because, okay, look at this plot I have put on the bottom left. This one is supposed to represent the white cap reflectance as a function of the wind speed. And, you have all sorts of symbols for different types of measurements and the curves are, different attempts to model this variability. But as you can see, it's really, really scattered. So the difficulty here is the relationship between wind speed and how much white cap coverage you have in a given pixel. That depends on many things, including even the temperature of water, of course, the wind speed, but whether the wind speed is blowing in the same direction as currents or in the opposite direction, that's going to generate more breaking waves, all sorts of things. So it's a very uncertain relationship, but unfortunately, that's the one we still use. That's what is between these brackets here, the function of wind speed, and multiplied by the effective reflectance of a white cap. And that gives you this OWC term. So basically, you have to keep this in mind when we use ocean color data, global ocean color data. Generally, there is a flag in the level 2 product that tells you whether the wind speed was above some kind of threshold or, well, there is something within the flag, within the quality flag, that you can use to maybe decide that, oh, okay, I'm not going to use this data point because the wind speed was so high that the uncertainty on the white cap correction is really, really big. So that's what it is. No one has come with something better than this. It's a difficult problem. So yeah, one option for future work, I guess. Another thing which we didn't look at so far with him are these transmittance, so the big T and the small t. So again, the capital T, direct transmittance for, that's mostly for the sun glint because it's a very directional and some sort of collimated signal. And the small t, well, diffuse transmittance to express how a diffuse signal that the water-leaving radiance is transmitted through the atmosphere. Same thing for the whitecaps. Okay. So, and there are different, there is another one which is, by the way, not included in this equation, but we will come to this a bit later. So this is just a sketch supposed to express what this diffuse transmittance is. So you see different pixels, LW going to the sensor. Part of it is scattered out of the way, absorbed. So that's the transmittance. But this one is supposed to express the fact as well that there are maybe some signal coming from the neighboring pixels, which is going to be scattered in your field of view. And this diffuse transmittance is supposed to account for this somewhere. So, but basically, that's the ratio of LW at the top of atmosphere, or what's left of LW at the top of atmosphere, divided by LW as it is just above the surface. The direct upward transmittance, the one we apply to the sun glint, when the signal comes from a narrow range of directions, it's very much simpler to express as the exponential of minus the total optical thickness divided by the cosine of the view angle. But there is another one that we use to normalize things and calculate maybe sometimes the reflectance, is the downward atmospheric transmittance for irradiance, which is basically the ratio of the downward sun irradiance that you will have at the sea level divided by what it is at the top of atmosphere. So basically the extraterrestrial irradiance multiplied by the cosine of the sun zenith angle. So the ratio of the two is as well the transmittance, an irradiance transmittance, and it's used during the normalization process of reflectance. So so far, quite often the approximations are used to calculate this transmittance. So the small t, so the downward diffuse, no, not downward. It should not be TD. Anyway, well, that's the diffuse transmittance. So as you can see, it's again, it's function of the optical thickness, single scattering albedo, and this little f is the forward scattering probability for Rayleigh with the R and for the aerosols. Very often these parameters are taken as constants and the equation is simplified. Okay. Okay, that's what is expressed. So yeah, let's simplify this way because omega is 1 for the Rayleigh and f is 0.5, so that you end up with 0.5 times tau r. And for the aerosol optical thickness, for the aerosol component, this 1 minus omega f for typical type of aerosol, maritime aerosols, you end up with a coefficient of around 0.2. Yeah, and the first term, oh, by the way, yeah, that's something I forgot to mention. There is an optical thickness for the absorption by atmospheric gas. That's something I didn't mention, I forgot that. Everything I told you before generally is done after the total signal that you get from the satellite, from the sensor, is corrected for gaseous absorption. It's because most, if not all, of the radiative transfer calculations we do to generate the lookup tables for the Rayleigh, for the aerosol, and so on, we do them for gas-free atmospheres. So we don't put any ozone absorptions, NO2, oxygen, whatever. So then, of course, when you get the real signal, which is affected by that, you need to correct for this gaseous absorption. So that's something I didn't really mention. But yeah, keep in mind that's one of the preliminary steps, of course. The thing is, this expression you see here is so simplified. It's an approximation of the transmittance. And the question is, well, whether this is a good approximation or not. Well, I did some time ago, I did some calculation with this. And what you see here on this plot is the comparison between the transmittance calculated through a Monte Carlo simulations with a sun zenith angle of 30 degrees and via this simplified expression, which is here. Each of the plot is with the vertical axis is, I think, the sun. No, no, that's the view angle. Sorry, from 30 to 80, and the horizontal axis is the azimuth difference. And you have the scale here, which is in percent. It's a percent difference between these two expressions. And the various plots are for all the top row is for in the blue for 43, and the bottom row is for 555 nanometer. And from left to right, it's for increasing aerosol optical thickness of 0.1, 0.2, and 0.6. And well, as you can see, there are quite significant differences actually. So I think that's one of the reasons why I think, for instance, the oil-chip processing now is no longer using these expressions, but they are using lookup tables from radiative transfer again to calculate the transmittance. The other thing you might notice here, or maybe if I start here, the geometry is only coming as the view angle, only. Here there is view angle and azimuth difference. And this is making a difference. The error is not the same. It's actually because you remember I told you the diffuse transmittance is supposed to account for the fact that in a given direction, actually you are going to receive some signal from the neighboring pixels. So actually the azimuth difference the relative azimuth is making a difference. It's not huge, but it is. So, if you want to be very accurate, maybe you need to account for that. But same thing, but now the sun zenith angle is 60 degrees. Something happened with the slide. And the difference are a bit larger. As expected, it's always the same, when you have more photons traveling for along longer paths in the atmosphere, any error is getting larger. And this one is a bit the same, but it's now for the big T, or the direct transmittance. And in that case, let me check this one. Can we use the? Oh, no, sorry. Can we use T, the equation for the small t, actually to calculate the capital T? Basically, what this slide says is, well, when the view angle is relatively small, maybe, but it's very often not the right thing to do. Okay, so just I close this parenthesis on the parenthesis or this small part of the transmittance. But sometimes in this kind of relatively complex processing, we concentrate a lot on some part of it, and we have been concentrating a lot on how to derive properly this atmospheric the aerosol signal and how to extrapolate it in the best way, reducing all sorts of errors. Transmittances have not necessarily been subject to that much scrutiny, I would say. So I think that's still where some of the large uncertainties and errors come in our ocean core processing. So maybe that's something to have a look at as well, a bit more carefully in the future. Sorry. Adjacency effects. So that's another difficulty for atmospheric correction when you look at a dark target, which is what generally a water pixel is, and just close to it, you have a very bright target like a cloud or a landmass, a bright landmass. So why is this? Okay, that's the problem of adjacency effect. You recognize this plot I showed you before, which is expressing, all the possible interaction in the atmosphere. And what is figured here is the width of maybe your pixel. And so what you think you are measuring is, LW coming from this pixel. But you have neighboring pixels, and you have some of the LW from this pixel that can be scattered in your instantaneous field of view. And actually, that's happening everywhere. The adjacency effect is happening anywhere in the oceans and everywhere. It just doesn't matter generally because the two pixels or the few pixels which are neighboring the one you are interested in have basically the same property or very similar property as the one you're interested in. So it doesn't matter if there is a bit of signal coming from the neighboring pixels, it's the same signal. When it becomes a problem is when these neighboring pixels have a very different signal and generally a much brighter one. Because then, of course, if a bit of this very high radiance from a cloud is scattered in your direction, you're going to make a big mistake, a big error on what you derive for this one. Okay. The problem with this is, of course, you don't know. Okay, if you have clouds around, well, you don't really know their reflectance. Sometimes you may even have a sensor which is saturating over this pixels. So you have no way to know what that signal is, maybe to try to do something to correct your pixel of interest. Oh, sorry, I'm talking about else already. So anyway, that's a difficulty. There are some algorithms that have been developed for this. It's complicated because, again, you would need to know exactly what the reflectance of this bright target is. You need to know as well, very well, about the atmosphere. So it's a bit of chicken and egg situation because you would need to know well again, the aerosols and the scattering and everything, which you don't know because that's what you try to derive with your atmospheric correction. So that's a difficult issue. It's, of course, there is a way to ignore or to, it's to just avoid processing or keeping anything which is too close from the bright target. So if you can identify clouds in an image, maybe you will make a decision that any pixel which is, a band of maybe 2, 3, or whatever pixels around this cloud, you eliminate them as well because you know that you are going to have a problem there. Same thing with the land, but that's a very crude assumption, of course. Yes. I have not included a reference to an algorithm, but there is one in particular which has been developed, I think, in the frame of the OCR as well. Yeah, sorry, the thing I wanted to add to this, it depends as well on the spatial resolution of your sensor, of course. If you have a very moderate, you look at, I don't know, kilometer size pixels around the cloud, you're not going to eliminate tens of them, maybe, and if you work with very high resolution sensors, maybe the impact is going to be a bit larger. And you can figure this out as well, by looking at transects across your image and seeing whether you can figure out how far the impact is away from the bright target. Okay, then we have this problem of turbid waters. Okay, everything we looked at so far is when the near infrared signal is negligible, and of course we know when there is quite a lot of scattering in the water because of particles, this is no longer true. So two main options here. The first one is, well, let's try to find another part of the spectral domain where the assumption of LW is 0 is still valid. And that's where the shortwave infrared is coming into play. So wavelengths a bit above 1 micrometer. We'll see this. But then the other option you have is to go back to this kind of spectral matching or all sorts of different techniques, but basically by incorporating a bioptical model for the marine components, and then using all sorts of techniques to generally iterative techniques, or that can be with neural networks or whatever, but to disentangle what this marine contribution is in the near infrared, and then maybe you can remove it. That's an option. If you find a way to derive this, and that's what the Olchi processing is doing. That's what they call the bright pixel atmospheric correction. So they try to first assess what this contribution in the near infrared is, then you can remove it, and then you end up again, you go back to the situation where you have a 0 signal in the near infrared, and you can apply the normal type of atmospheric correction. Or you don't do this, but you just do some sort of a spectral matching to disentangle the marine and atmospheric signal. So going to the SWIR bands, it's just because, when I showed you the water absorption plot a bit before, I think it was going up to 800 nanometer only. This one is going much further. And as you know, there is orders of magnitude more absorption by water. So if you go to this wavelength here, which are the one used in this SWIR-based algorithms, again, you have so much absorption that you can go back to the assumption that the water's leaving signal is 0. So that's in particular what Menghua Wang has been developing. And yeah, that's one example here. Yeah, that's just to give you a detail of the reference. And of course, you can as well combine the two, the near infrared and the SWIR bands, and try to see what happens. So on this plot, you have the columns of our chlorophyll and the NLW in the blue and the green, so 531 and 551. The top row is for the standard near infrared method. In the middle is the SWIR method, and in the bottom, they have tried to combine the two. And what you can see basically is, all these white areas here in the near infrared method, it's just basically where the method completely failed, or it's just nothing. And when you move to this SWIR technique, so you still can get something. And but maybe what you get then for the offshore area might not be that good, because that's not what the SWIR method is supposed to do. So if you combine the two, maybe you get some kind of a better picture. You can see with the SWIR method, here it's very noisy above the clear waters, or the clearer waters. But in that area, there are not really any clear waters. But when you combine the two, it's better. Because one of the difficulty with this is, of course, you go further away in the spectrum. Okay, good. You then are again in this situation where you have 0 signal in the near infrared. You determine the aerosol signal, but then you have to extrapolate this signal over a much larger spectral range to go to the visible. So any error is going to be amplified even more than when you do this from the near infrared. So, there are always pros and cons in any method, and that's what this one is doing. Actually, there is another part of the spectrum that has been attempted to be used to do this for turbid waters, is actually the near UV bands, because in some situations, because it's no longer so much because of the water absorption. Okay, water absorption is minimal in the blue, but then it starts to re-increase when you go to the near UV, but it's not as large as it is in the near infrared. but then you may have a lot of CDOM absorption, okay? So you end up at the end with nearly no signal because of this. So you have the possibility sometimes that you have an anchor point in some way in your spectrum, which you go to the near UV, where the signal is so small because of absorption by CDOM and whatever that you can use it in a bit again like a dark target. So Xiangqiang He and colleagues have developed this. I'm not sure if it's been in any way implemented operationally in any mission, but that's one option actually that they have tried. So maybe some of the Chinese ocean color sensors have included this in their processing, but we don't really know. And that's illustrated here with this normalized water-leaving reflectance spectra in different situations where you can see that around the 350 nanometer, there is not much remaining. It might not be exactly zero, but at least, and you can understand if you have a way to constrain the problem in the near or SWIR and another constraint at the other end of the spectrum, that might help you to adjust the system properly. And this is the application they did. So it's for the 9 plots on the top of for the wavelength from 412 to the near infrared. And what they have put at the bottom as a comparison is what would be obtained using the classical near infrared bands. And the bottom is only for 412, 443, and 488, which correspond to the plot on the top here. No, yes. In that case, it's quite different, but I'm not sure actually what they would point to show us the very big advantage of the near UV. I just mentioned it because it's an option. It's not. I think there are still some challenges behind this, which is why maybe it's not been implemented more widely for current missions. Okay. Everything we had a look to the progression from the early algorithm of the CCCS, single scattering, moving to multiple scattering, and using all these aerosol models. Well, that's what we do at the moment. That's what most, all the NASA missions, ESA, and again, most of the current global missions basically follow this kind of logic. But one thing to keep in mind is atmospheric correction is not about deriving aerosol properties. We don't care in some way. We use this because it's a convenient way. It's a way that has been found to assess the contribution in some part of the spectrum and to extrapolate to the rest of the spectrum in a reasonable way, so we can get LW with good accuracy. But whatever you can do, which would lead to the same quality at the end, and which would not use at all any aerosol model, would be fine. And that's exactly what this algorithm that I showed you now is doing. It's called polymer. It means polynomial-based algorithm applied to Meris, but it's actually can apply it to all sorts of processor, and that's what the ESA Ocean Color Climate Change Initiative is doing and applying to all sorts of sensors to generate multi-sensor merge products. And in that case, the total reflectance, okay, it's first corrected by for sunlit and molecular scattering, and then you end up with relatively simple equations where your reflectance is, this again, this AG here. What does it mean? Well, that's the atmospheric path radiance, basically, and the reflectance, water-leaving reflectance. And this atmospheric part is simply expressed as three components. One which is the glint, one which is aerosol, and one which is the coupling between all that stuff. Anyway, yes. No, it's, yeah, whatever. Yeah. Generally, it's expressed in terms of reflectance, but you can express everything in terms of radiance if you want. That's basically the same. Yeah, no, yeah. Yeah, the relationship between the two is unequivocal. And then this atmospheric term, in some way, is expressed as the function of three basic terms. One which is spectrally flat, and that's supposed to take care of things like sun glint, thin clouds, or anything bright, any sort of bright target that would be in the field of view. The second term in a lambda -1 is supposed to take care of the aerosols, more or less. And the last one is lambda -4. It's for the way more spectrally dependent Rayleigh scattering. And basically what's happening is these coefficients C0, C1, C2, they are estimated by a least square fitting of the observations, where the ocean reflectance, or the ρw, is modeled as from a bioptical model. So we come back to, the logic that we had initially with the CCCS. It's basically the same with a more sophisticated way of representing the atmosphere. But it's again the same logic. Now you do sort of a spectral matching. But then in that case, we don't care about aerosol models. There is no need to this. It's just another way to practically make this correction and derive the atmospheric contribution accurately. And it works really well. The reference are at the bottom of the slide. And, just an example here. So the total signal on the top left, the chlorophyll in the middle, and what is this? The last one. Looks like it's chlorophyll as well. Sorry. I guess this one was supposed to, yes, I know what it is. Sorry for that. The polymer results is on the right side, and in the middle you have something, it's probably the classical Olchi-Meris algorithm. And that's to show that this algorithm is actually very good to improve the coverage, because it has this capability to process and still derive reflectance relatively accurately, even in relatively difficult situations where normal type of algorithm would fail, like sun glint and turbid waters and even very thin clouds, which is what you see on this situation. Okay, and yeah, it's been used to derive some composite. This one is a composite over only 3 days, so you can see that the improved coverage that this algorithm has provided is really good. You would not have the same coverage after 3 days of Meris data with this. Okay. The difficult problem of absorbing aerosols. Here I have put, just illustrations of this, one of the main type of absorbing aerosol, which is causing difficulties for ocean color. They are this desert dust. The example on the left is showing you in the Mediterranean Sea. Interestingly, there is as well on this one, you have another type, which is at that time, the Etna was erupting. So you have this volcanic ash coming from Sicily, and it's very, very clearly visible on this one in the middle. And this one is, what we very often see on this big dust storm coming off Western Africa and crossing the entire Atlantic. So anyway, so first thing, their optical thickness is relatively high. and they are absorbing. So they are making our life difficult with ocean color. So you remember particle size distribution, index of refraction. So again, same thing. The desert dust here is on the right side of this plot. So you clearly see the distribution of the, so here it's in unit. Why do we have more large particles here? It's a bit unclear. They are all absorbing aerosols, so they have single scattering albedo, definitely significantly lower than 1. This particle size distribution are a bit confusing to me now because this one has much more large particles. Well, some of them are actually, okay. Anyway, so what's happening with this? When we work in the near infrared, it happens that we cannot really discriminate between this type of aerosols and the others because their absorption property, their significant absorption is essentially starting for lower wavelength and increasing toward the blue again. So when you look at the near infrared, you have no idea. So then you will select, in your lookup tables, if you might generally select a more classical type of, just based on the spectral dependence between the two near infrared bands, might select a maritime or a continental type of aerosol, whatever. But then you will be completely wrong with the absorption properties in the visible, and then you are going to overcorrect the signal. Because of course, the atmospheric signal is lower when there is a lot of absorption by aerosol. And if you ignore that, you're going to overestimate the atmospheric part. And when you remove it from the total, you end up with an underestimated reflectance, which can even sometimes become negative. Well, when it becomes negative, at least you know something is completely wrong, so you can eliminate that. But if it's significantly underestimated but not negative, that's where you have a problem. And as I told you before, the issue as well is that the altitude and thickness, by the way, of this absorbing aerosol layer make a difference on the top of atmosphere signal. So these two plots are expressing this. They are simply the error in the reflectance in the blue. And, the M80 is a maritime aerosol, M80 as well. T80 are terrestrial aerosol with some absorption, not so much. But the difference between these curves is when these aerosols are uniformly mixed in the entire atmosphere or just put in 2 layers, just to have a rough idea of the impact of the vertical distribution. So in that case, the error is really minimal because these aerosols nearly do not absorb. On the right side, it's the same, but with absorbing aerosols here. You can see that the error is becoming really important. So thickness of the layer and where it is placed in the atmosphere. So again, one solution that was developed for this is, again, spectral matching algorithms. So similar logic, a model for the ocean properties, a model for the atmosphere, and some sort of an iterative process to separate the two and do a better correction. So that's what you see here. The left image is when using, the standard type of correction. So you see there are plenty of areas where nothing can be retrieved, and the spectral matching algorithm on the right side where things are much, much better. Okay, so yeah, to summarize again, that's definitely one of the big challenge for ocean color. Well, not that we have, absorbing aerosol everywhere in the oceans, but still, it's significant areas. It happens as well that some of these areas are high productivity zones of very high interest. This one on the Western Africa, that's all the upwelling, Western Africa upwelling. That's a very, very productive area. That's the where a lot of fisheries happen. And yeah, that's important areas we want to monitor properly. So doing a better job with this absorbing aerosol would definitely help. And for that, well, there are some options. If you have independent information on aerosol, that might help. But again, always keep in mind that the atmospheric correction problem is different from the derivation of aerosol properties. So the way proper derivation of some optical properties of aerosols might help the atmospheric correction process is not always that obvious. I might come back a bit onto this a bit later. This thing, we mentioned that a bit before. That's one of the difficulty when we move away from the medium resolution sensors and we want to use, the Sentinel-2 MSI and Landsat and all sort of sensor like this with high spatial resolution. So I'm not going to spend much time on this because we already discussed it actually before, but that's definitely a difficulty. So I think quite often what is done is to ignore this kind of models and use the signal itself, try to identify this bright sunglint contaminated pixel in an image. Okay, when you have done all of this and you think you have been doing a very great job in developing your algorithm, now you need to validate this and to be sure that you're doing the right thing. So I would say, and that's what is on this slide, that you have maybe two main ways of doing this, which are not exclusive, of course. Well, the first thing is to validate the end product, so the water-leaving radiance, or maybe the chlorophyll, even if you don't care about the water-leaving radiance, you just want to look at the chlorophyll. So what you do, why you know that, you do as many good field measurements as you can, try to match them up with the satellite values, and you end up with this kind of analysis. So scatter plots, histograms, you can generate some statistics and see whether you are doing well or not. Might tell you as well in what part of the range you may have a problem, maybe for clear waters, maybe so. Okay, so there is a lot of this happening in our communities. Space agencies have been trying to help quite a lot with this to make all this data that we use for validation as consistent as possible among the different groups. So it's a big effort. And it's a never-ending process, of course, because we launch new sensors, we improve algorithm, we change this, we change that, we recalibrate. So you always need to have this validation data. So that's a significant part of the activity of remote sensing people is to go at sea, actually, not only being processing data on computers. Yeah, and the other thing you can do, validating the quantities that the atmospheric correction produce, so basically the past radiance, that's a bit tricky because in that case, you say, look, I want to, okay, water-leaving radiance is one thing, but I want to see whether the atmospheric properties I have derived are correct. So you can do this. Some people have tried to do it. It's not been very much used, but I wanted anyway to mention this. So basically, what you are going to do is to use this kind of sun photometer systems, which is on the ground, measuring sky radiance and trying to compare this radiance, this past radiance that you can measure from the ground to the one you have derived from your satellite system. The difficulty you have in that case is to find the geometries where you can sample the same scattering angle, which is not that easy because in the satellite configuration, the sun is basically on your back, the sensor is looking down at the atmosphere. When you do this from the ground, you're on the ground, you're looking up, and the sun is not on your back, but in front of you in some way. There are some ways to combine geometries so you have a relatively similar scattering angle at the end, and that's what these guys did. And you have the comparison here between the horizontal, which is the sky radiance from this sun photometer from the CMED, and the simulated downwelling radiance on the vertical axis. So yeah, that's probably a theoretical exercise from simulated radiance. But again, I wanted to mention it because that's an option. But there is maybe in this a bit of, to me, a bit of again confusion between aerosol remote sensing and atmospheric correction. Well, another example of validation of byproducts of the atmospheric correction. So in that case, that's for CWIFs and MODIS, and that's the optical thickness for the aerosol optical thickness at 443 nanometer on the top, and on the bottom it's alpha, which is, I think, in that case, the spectral slope of the aerosol scattering for different sensors. And that has been done at the AAOT, which is the Aquanta Tower in the Adriatic Sea. So that's in a relatively coastal environment. Yeah. Okay, actually we are coming to the end. Yeah, it's again, but it might seem a bit pedantic to make this distinction, but I think it's quite important actually. That to keep in mind that atmospheric correction of satellite ocean color geometry is not aerosol remote sensing. Well, we had this example. We looked at this polymer algorithm, which is not using any aerosol models or whatever, not deriving any aerosol optical thickness, and it works pretty well. And one of the simple way of seeing this is, what the ocean color community try to eliminate from the signal is what the aerosol community is interested in. Of course, there's first this main difference. But again, as was reminded previously, the goal for atmospheric correction of satellite OCR is the extrapolation of the aerosol signal from the near to the views. And whatever method you can use for this, whatever it's a physics-based method or maybe something completely different that you would find and that would work well, it's okay. Interestingly, you may do this well, this extrapolation, and still have some of the byproduct of it, like the aerosol optical thickness, which is generally produced as an outcome of the atmospheric correction. You might get it wrong, and still your atmospheric correction is going to work well. Okay. I have said why here, but I'm not asking you to answer this now, because I guess it might be a bit confusing. But one of the reasons, again, is about the geometry of the problem and basically what part of the volume scattering function we are looking at. When we said this a bit before, this was a bit difficult, is because looking from the ground or looking from the top, it's hard to be in the same geometrical configuration. But you might get a wrong aerosol optical thickness and still go a good extrapolation. Why? Because if the important parameter in this extrapolation is the spectral dependence of your atmospheric signal. If you get this right, all good. That doesn't mean that the inversion you do in the near infrared is going to be very accurate in terms of aerosol optical thickness, for instance. So well, I will stop on this because maybe it's more confusing than enlightening.